All right, let's jump into one of the coolest and most dynamic topics in all of precalculus, parametric equations. If you've ever wondered how math can literally tell a story of motion with a real beginning, a middle, and an end, then you are in exactly the right place.
Seriously, just think about your favorite animated movie or any video game you play. Every single character, every explosion, every little moving pixel on the screen follows a super precise path. So, how do they do it? How does an animator tell a point not just what path to follow, but when it needs to be at each exact spot? That question right there is what this is all about. And the answer is parametric equations.
So, up until now, you've probably always described curves with good old y equals f of x. And look, that's great. It works. But it has one massive limitation. It's like it gives you a map of all the possible roads, but it doesn't give you the GPS directions. It shows you the path, but it doesn't tell you which way you're driving or how fast you're going. And this right here breaks down the difference perfectly. A standard function just gives you that static path. It's the map. But parametric equations, whoa, they give you the entire journey. They tell a point where to be, and just as importantly, when to be there. It's literally the difference between a drawing of a racetrack and a video of the actual race. Okay, so if we're going to tell these amazing stories of motion, we need to learn a whole new language, and that is the language of parameters. This is what lets us add those two crucial ingredients to our graphs, time and direction. The absolute star of the show in this new language is the parameter, and we almost always call it t. You should just think of t as our master clock. For every single moment in time t, it dictates the exact x and y coordinates of our point. It's kind of like this hidden variable pulling all the strings from behind the scenes. Now, this is where it gets really, really cool. As ticks forward, as time passes, our point has no choice but to move. It's on a journey, and that journey gives the curve a direction, what we call its orientation. We show this with little arrows right on the graph. Those arrows tell the entire story. Here's where it started, here's the path it took, and here's where it ended up. And of course, every story has to have a beginning and an end, right? Well, that's where the domain comes in. The domain for our parameter t is basically the start and stop button for our story. Are we watching for just 5 seconds or for an entire hour? The domain tells us exactly what part of the journey we actually get to see. Okay, enough with the theory. The best way to really get a handle on this language is to just use it. So let's get our hands dirty and actually plot a path, step by step. So here's our first mission. We've got our equations, you can think of them as the rule book for our points motion, and we've got our time interval. We're going to watch this little story play out from time t equals 0 to t equals 3. First things first, we just need to build a quick table. It's super simple. We plug in our t values from the domain, 0, 1, 2, and 3. So at time 0, boom, our point is at 0, 1. 1 second later, at t equals 1, it's already zipped over to 2, 2. See how that works? Every tick of the clock, t is telling the point its new x, y address. Okay, now for the fun part. We plot those points on the graph. We connect the dots, and what do we get? A nice, simple line segment. But wait, we're not done. This is the most important part. We have to add an arrow to show the direction of motion. It's moving from 0, 1 to 6, 4. That little arrow, that's what tells the story. All right, that first example was a nice warm-up. Let's try something a little bit spicier. This time, our x is t squared and y is just t. And our story is going to run from time t equals -2 up to +2. Any guesses what kind of shape this one's going to make? Now, here's a really neat trick you can use sometimes. If you can, try to eliminate the parameter t, just to see the underlying shape you're dealing with. In this case, since y is literally equal to t, we can just substitute y directly into the first equation. So instead of x equals t squared, we get x equals y squared. And hey, we know that shape. It's a parabola that opens sideways. So the process from here is exactly the same. We build a table, we plot the points, and just look at this motion. Our point starts down at 4, -2. Then it gracefully sweeps in towards the origin, hits that turning point, and curves right back out, ending at 4, 2. The arrows perfectly captured that beautiful symmetric flow. Now, as you start playing around with these yourself, there are a couple of common traps people fall into, so I want to give you a few pro tips to make sure you're always telling the right story. Pro tip number 1, and this is a big one, always check the domain. Seriously, don't ignore it. Changing the interval for t is like showing a different scene from a movie. You might get a much shorter journey or see a totally different part of the path. It defines the beginning and the end of your story, so pay close attention to it. This is a huge one. Pro tip number 2, do not forget the direction. Forgetting the direction arrows is like showing a picture of a roller coaster track without the cart. Is it going up the hill or screaming down it? The arrows are absolutely essential. They're what turn a static shape into a dynamic journey. So don't forget them. And finally, remember that t itself does not appear on your XY graph. It's the clock, not a location on the map. It's the input, the independent variable that's working in the background. It tells you when something happens. The output, the position, is the XY point that you actually plop. So after all this, you might be thinking, okay, that's kind of neat, but why does it all matter? Well, remember that question we started with about animation? It's time for the big payoff. Let's connect this math directly back to what we see on our screens. And this is not an exaggeration. This is literally the engine that drives motion in computer graphics. From the way a character jumps in a game to the path of a spaceship in a movie, it is all controlled by the language of parametric equations. Here's how it works. An animator or a programmer defines a path using an x of t and a y of t. The parameter t then becomes the frame number of the animation. So for frame 1, the computer calculates the position. For frame 2, it calculates the next position. You string thousands of these points together, and you get that perfectly smooth, believable motion. So as we have seen, parametric equations are so much more than just another way to draw a graph. They are a powerful tool for storytelling. They describe a complete journey with a path, a direction, and a timeline. So the real question to leave you with is this. Now that you understand this language of motion, what stories could you bring to life?